says what the schedule says. I'm not sure whether my slides will agree with that. Okay, let's say 30 year out.
Okay, welcome to the afternoon session. So we are happy to have Slobodan and Mitrovic. We'll talk about sublinear algorithms for correlation clustering.
Thanks a lot. I appreciate this. Thanks a lot for the organizers and for this great opportunity. I'm really happy to be here and surrounded by so many nice people and familiar faces. Today, I will tell you something about sublinear algorithms for correlation clustering, and the whole presentation will be based on a very recent work by Mina Dali-Ruifart from Morgan Stanley Research, Kostya Makarice from Northwestern University, and this is where my face goes. So okay, great. So let me start by defining what the problem is. I will not assume that everyone knows about correlation clustering. That I will define the problem, then talk about a very cute and elegant algorithm for this problem. So what is correlation clustering? It was introduced in 2002. In this problem, you're given n objects, and there is some similarity function f. And I will show you in a moment what is this. But this function f receives on input two objects, A and B, and simply tells you in this like binary fashion they are similar or A and B are dissimilar. So if you model this as a graph, then we have these n objects, I guess 11 of them, and then whenever there is this full edge, solid edge, a green edge, these two objects means they are similar. And whenever for every dashed edge, and also when there is no edge, I didn't want to clutter this graph too much, but also when there is no edge, in this example, I mean two objects are dissimilar. As you can see immediately, we can think about this simply as a graph, right? And we have edges. And in a typical setting, we keep only these solid edges. But if there is no edge between two vertices in the graph corresponding to objects, we think that these two vertices or these two objects are dissimilar. So this is the input. What you would like to solve? Well, we would like to find some clustering which intuitively and very informally speaking aligns with f as much as possible. Right? There are different ways to define what to align mean, but the one we will use in this example is simply as follows. So if you take a clustering like this one, we have 3 clusters. What would be the cost of this one? Well, for every edge like this one, which denotes dissimilarity between two objects, but this edge is in the same cluster, we would pay 1. So in this case, we have this edge, which is the similarity edge, and it is in the cluster, and also this edge. So we're going to pay 2 for this dissimilarity edge. We're also going to pay for every similarity edge, for every this solid edge which spans different clusters. And in this case, there is only one such edge, okay? This green edge. So we pay 1 for this edge, and the cost of this specific clustering in this example is 3. And our goal is to find clustering which minimizes this cost. Okay, so that's the problem. It has some practical applications and motivations as well. Actually, even the first paper mentions these two. One of them is aggregating accounts. You can think of each of us having accounts on maybe different platforms. I'm not saying, by the way, applications are all for good use, just talking about applications. So you might have multiple accounts, and then you want to ask, okay, what accounts correspond to the same person. In this language, it would be the accounts which end up in the same cluster. There's also this application, nice application in semi-supervised learning, where you sometimes you're able to design this function f without actually knowing labels of the objects. But then if you get the clustering and you want labels, you can ask for label of only of some of those objects in the cluster. Now, if you get this cluster and I tell you that these two objects are shoes, it's, I think, fair to assume that all the objects in this cluster have something to do with shoes. Okay, so these are two applications, and one of the reasons why it seems people care a lot about this practice as well. I like this as a problem in theory. I think it has very nice structure, but people in practice like this problem as well. And there has been lots of work on this problem. In particular, so this problem is, it's can be hard, but the question is how good approximations you can get, and there has been lots of work. There is very elegant approach from 2005 by Elon, Charikar, and Newman, which gives three approximation. I will describe this algorithm, like very elegant and cute one. And there has been additional work trying to get better and better approximation. And as you can see by the years, and these are even not all the papers, a lot more activity happening over the recent years. And I believe in the last paper, the best lower bound they have is 1.042 hardness of approximation. And they also show that 4/3, you cannot beat 4/3 if you're using LP clustering-based approaches. What in this talk we care is about algorithms which are not only good in terms of approximation, but they're also, and I will use this term, they're also efficient in big data regimes, or at least what we like to connect to big data when we write papers and motivate our results. So one of those setups is massively parallel computation. People have been trying to get good approximation, but also to execute this in as few rounds as possible. You don't know exactly what MPC is, it does not really matter. I'm not going to use MPC in the rest, but I'm listing this just as one line of results. Another one is local computation algorithms, where people trying to solve this problem to decide what is the clustering of one specific vertex and to reduce the number of these LCA probes or LCA queries in graph, and also ideally to get small, some nice approximation. I should mention that this is not complete picture. Those of you who know pivot, it's the same as randomized greedy MIS, and there has been more work on randomized greedy MIS, but I will get to that. And then another interesting regime is dynamic. So the result that we get in this work gives you, if you think of epsilon as being small constant, it gives you constant update time in the fully dynamic setting, but under oblivious adversary. So there are a few results. That you get out of this work. Some of them got improved after this work was published. Some of you might ask about the semi-streaming. This is also a classical setting for kind of big data computation. Our algorithm does translate to semi-streaming as well, but it matches existing state of the art. Particularly, there were these two results by, say, Kambuskun, Lindy, Pai, and Yara, and another one by Chakrabarti and Kostya Makarichev, who gave 3+ epsilon approximation in single pass. We do not get anything better than that, but it just matches state of the art. So this is roughly about the history. And then my goal in the rest of this presentation is as follows. I want to show you this pivot. Many of you might have seen this. I think this is really, if you're interested in correlation clustering and you want to get something out of this talk, this probably would be this algorithm itself. Then I will tell you what is our approach, which we call pruned pivot, and it is built on top of pivot. It's very small modification to pivot. And then I will switch to maximal independent set. But I will get to this, and then hopefully give you analysis. Hopefully give you full analysis of one part of the algorithm. Okay, let's go to pivot. So the algorithm is as follows. You get this graph G, and again, in the language of the first slide, the set of vertices are those objects. E is the set of edges, but there is an edge between two objects if and only if they are similar. Here is what the pivot does. It first orders the vertices of the graph randomly, uniformly random permutation of all the vertices, just takes one permutation. And then it visits vertices one by one. And if a vertex is not clustered yet, it takes that vertex together with its unclustered neighbors, puts in the same cluster, and this is just repeated. Okay, so that's it. So here is an example. Assume that the ranks or these pi values of the vertices, this is 1, of this vertex is 2, and so on. So what this algorithm would do, well, 1 is the first vertex. It would take that vertex, it's not clustered. It would label that vertex as pivot. Whenever some vertex passes this if, we call also this vertex pivot. And it will put together in the same cluster 1, 3, and 7. And from this point on, 1, 3, and 7 are all clustered. And we look at the next vertex with respect to pi value, it's 2. We also label this as pivot, and we put 2 and 9 in the same cluster. 3 is clustered, so we just skip 3. Then we look at 4, call it pivot, cluster with 9. And notice that 3 is still clustered with 1. It did not change the clustering, it's still clustered with 1. And then finally, we look at 6 and cluster 6 and 8, and 6 is also pivot. Now, surprisingly, this simple approach gives you 3 approximation. And I really recommend looking at the proof. And one of those proofs, I feel there is one part, very subtle part. You have to wrap sort of your mind around that, but then it becomes, really natural and really nice proof. And we know we can get the approximation for that. This one gives you the approximation. To describe you our approach, I want to look at this same process, but in slightly different way. Okay, exactly the same process. And this is recursive query way. If you have ever worked with LCA, what I'm going to describe is just LCA version of this pivot algorithm, nothing else. But here is what I mean. Say that I want to ask what is the cluster, who is clustered with vertex 9. I only want to learn about 9, right? So how I can do that? Well, I look at 9. I know that the vertices are visited with respect to these ranks or pi values. And I'm going to look at the smallest. I don't know what is the cluster of 9, but I'm going to ask 3, which is its smallest, which is its, we say, highest rank neighbors, or the one that has the smallest pi value. We will ask what is happening with 3. Is 3 maybe a pivot or not? Because if 3 is pivot, then these two would be clustered together. Well, 3 doesn't know whether it's pivot or not just by looking at itself. So it again looks at the neighbors. It looks at 1. 1 is the smallest. 1 has the smallest pi in its neighborhood, so it is a pivot. Okay. Then it tells back to 3. Well, you're not pivot. We are clustered together, but you're not pivot. Well, 9 still didn't learn what is its cluster. It needs someone in the neighborhood to be pivot, so it asks 4. 4 goes to 3. 3 goes to 1 again, and 4 is now pivot, and we learn that 9 is actually clustered with 4. But if you like to think about this in terms of execution tree, this is what is happening. 9 queries 3, 3 queries 1, then recursion goes back, 9 queries 4, 4 queries 3, 3 queries 1. Yes.
Why should 3 go back to 1? use it to...
Okay, excellent. You can use that, excellent. So the question is, why would we have this in this tree? Because tree already has that information. The answer is that you don't need to actually ping. You can store this information. Surprisingly, what I will show you, it does not matter. Like you still can do this. You still can look at the full tree, and what I will show you, even if you're not trying to be careful about this, it's the same complexity. I'm not sure whether asymptotically one can actually improve everything if you kind of cache these kind of decisions, but you're absolutely right that in terms of practice, for instance, it would not make no sense to again do everything for tree. So our approach, pivot just runs this, and it runs the full tree. Eventually, it learns, okay, this is what's happening with 9. What we are saying, say that you want to learn about the cluster of 9, run this recursive query view, and as soon as the tree size gets size 1 over epsilon, order of 1 over epsilon, stop. Say, well, 9, I will take 9 to separate singleton cluster, and I will stop execution from there for the vertex 9. So that's it. This was helpful to show you this view on the process, because then it's easy to define what our approach does. And you can, again, show that this gives you 3 plus order of epsilon approximation. I want to mention, to contrast these two results known before this work. There is this paper by Benejad, Sohail, Charikarma, and Tan from 2002. They show that if you also consider this tree query process, but then you truncate at the depth 1 over epsilon, you also get 3 plus epsilon approximation, 3 plus order of epsilon approximation. There was this another result by Chakrabarti and Kostyama-Karichev, where they show that for every vertex, and say this recursive tree, it's enough if you consider only the highest ranked 1 over epsilon neighbors, and then truncate if you need more neighbors, make them singletons. It also gives you 3 plus epsilon approximation. And if you would combine these two, it would tell you that the tree size does not need to go beyond this. Now, I'm not aware of a black box combination of the two, but I'm very confident because we actually did that. If you take this as a base and then you open up this analysis, and Sohail is nodding, maybe he tried that as well, then you can actually show this. But we get only 1 over epsilon. Yes.
Once the tree gets large, you can forget about it.
Okay, great. Thanks a lot. Next slide. Thanks a lot. So when the tree gets large enough, why you can even expect that this thing that I showed you works, right? So that's the question. Why can you expect to be able to get some meaningful analysis? I will not give you full answer by this in the next slide, but just an idea. Then I will expand on something related. Well, say that say that there is another vertex W and pivot W and 9 are clustered together by pivot. Just assume that happens, but then the algorithm, this pruned pivot, actually this execution tree becomes too large, so it's not going to cluster 9 and W with pivot. It's going to make 9 singleton, so it will essentially cut this edge by 2 clusters. Okay, so if that happens, that's something that we do not like, because we are, compared to pivot, we are paying more. But it's not hard to show that that there are many edges in this tree, roughly half the size of this tree, that the pivot has to cut. So again, if you look at this tree with these red arrows, it's not difficult to show that roughly half of them pivot will cut. That roughly half of them, pivot will separate them in different clusters and will pay something. So the idea is to charge this blue edge to many of these edges which are cut by the pivot in this tree of size 1/epsilon. Someone might complain and say, well, we are not done because many blue edges can be charged to the same red edge. And you're absolutely right. We have to show that it does not happen. Luckily, it does not happen. And I will show you how we argue about this process. But this is roughly the intuition. So you're growing the tree size and so that you have many things to charge to. And then you're arguing that not too many blue edges are charged to one red edge. This is something which in prior work, I think it was called the width, right? Yes, the width property. I will just very briefly, so that was the approach. I will very briefly go over implementations in different models of computation. LCA, I think it's very clear, very direct, because this execution, this query tree, just by design, has size at most 1/epsilon for every node. To learn what are your highest ranked neighbors, you just need to scan your nodes, and so it gives you delta/epsilon, right? Without any extra effort. For MPC, it's similar if you are willing to assume that 1/epsilon to the in exponent 1/epsilon is small enough, because this is the 1/epsilon hop neighborhood around every vertex, where you are constraining every vertex to only keep its highest ranked neighbors. This information is enough for every vertex to figure out what is its clustering. So you can collect 1/epsilon hop neighborhood around every vertex, put it on one machine and simulate locally. Again, also just very direct implementation of the algorithm I've showed you. For dynamic, it's slightly more involved. Again, not too difficult, at least not the second part. So first of all, we can show, and this I hope to show you, in fact, in the rest of this presentation. Yes, we can show that in expectation, one edge is queried constant many times, where expectation is taken across all permutations. And this really helps in the dynamic setting. And the second thing that you need in dynamic is to be able to learn what are your k highest neighbors. And it's also not difficult. There might even be some off-the-shelf data structures which we simply didn't find. But it's not difficult, given that permutations that you're looking at, random permutation of the vertices. So I simply want to bucket all neighbors of a vertex into these ranges, like into the first bucket corresponds to my neighbors having pi value between 1 and n/delta2, and then this is how I propagate the buckets. The idea that in expectation, each of these buckets will have only one neighbor of V. So it's easy for me to fetch the k highest, the k top range neighbors. Anyhow, fairly simple exercise when you have this to go through the analysis and show that in expectation, indeed, you are getting order of 1/epsilon time. What I would like to do for the remaining 15-20 minutes is to switch to MIS and then give you the analysis. I will attempt to give you the full analysis so that you can walk away from this talk. And if you take pen and paper, you can just write down and fill out details. I have to say that I'm feeling a bit like on my wedding day while I'm saying this, making promises that I cannot certainly deliver. But let's see how it goes. Maybe it will be more surprised than my wife. So maximal independent set. Pivot, the algorithm, the pivot algorithm you've seen is exactly the same as randomized greedy algorithm for MIS. Those two are identical algorithms. And when we said that we label vertex to be pivot, in this randomized greedy MIS, it corresponds to saying that the vertex is in MIS. Okay, so that's it. And people have been studied, I would say quite extensively, at least in the sublinear algorithms community, how many local computation algorithms queries you need to graph to learn whether a vertex is in MIS or not. And then it means that there was, whoever studied, right, randomized greedy MIS, it would directly translate to LCA. And that's the missing references that I didn't mention. So let's now go over them. There was this really nice work by Nguyen and Onak in 2008. And they showed that if you execute randomized greedy MIS from a vertex, again, you're taking permutation of all the vertices, you're following this query process that I've showed you, and you need 2 to the order delta many LCA queries to learn whether vertex is in MIS or not. Then just a year later, there was this really beautiful work by Yoshida, Yamamoto, Ito, and they make amazing improvement. They show that actually, if you take a vertex at random from your graph, and then you ask the same question, how many queries you need to learn from this random vertex, whether it's in MIS or not, you need only order of the average degree. For some reason, there is bar here, but it's not showing. So it's average graph degree. Some very clever bijection that they set up. And then once you set up that bijection, somehow everything works as magic. And so, yeah, so that's what they get. Then there has been another type of results which are asking what guarantees you can give for every vertex in the graph and with high probability. I'm emphasizing here that this guarantee holds from a random vertex in the graph, or if you wish, it holds for vertices on average. But there has been a fairly long line of work trying to answer this question for any vertex, and again, with high probability. And the most recent result we have is that if you give me a vertex, any vertex in the graph, there is an LCA, which for that vertex with high probability tells you whether it's an MIS or not. I mean, it tells you whether it's an MIS or not, and the output is correct, consistent across all the vertices with high probability. And this was by Mose and Ghaffari, I think Fox 22. Why I even chose to talk about this, because as a side product of what we get from the analysis of this correlation clustering, this pruned pivot I've shown you, is we do recover the guarantee by this result from 2009. And I want to emphasize here, we are not getting, at least not that we see, let us know if you do see, we are not getting anything better than what these results get. But this is a community which cares a lot about sublinear algorithms. And I think it's fair to say that this approach in general has been quite influential. And we have different way of reasoning about whatever we are showing. So my frank hope is that some of you might find more application of this approach. And so that's why I choose, when it comes to analysis, to show you something that we already know it exists, but hopefully using different language and somewhat different view. Okay, I think I'm just perfect on timing. So let's go back to our example, and I want to set the process, very simple process, and how we reason about this analysis. So again, what I would like to show you, maybe let me say it again. At the end, I would like to show you that in this recursive query view of even pivot, if you do this for every single vertex in the graph, one edge in expectation across all permutation will be queried at most constant many times. So this is my goal. So this is our graph, and these question marks are their ranks before the algorithm. I want to think about the process where I know the topology of the graph from the beginning, but I don't know the permutation. And the permutation is revealed one rank at a time. So for instance, at time 1, I just see that this vertex has rank 1. I can immediately deduce that this vertex is pivot, right? Or equivalently, this vertex is in MIS. But I can deduce something more. I can also deduce that if I'm running that LCA recursive thing, these two vertices, which have these red arrows pointing to 1, are going to query 1. Because 1 has the smallest rank in their neighborhood, and we still don't know about these two vertices, whether they are in MIS or not. Okay, so I know something even more about the process. And at this point, I will say that these two vertices are settled. What does it mean? I will say that the vertex is settled when it learns which cluster it belongs to, or when it learns that it is in MIS or not. And at this point, actually, these two vertices, which we'll call settled, even though we don't know their ranks, we don't know their pi value, but we are certain that these two vertices are not in MIS. So I do a bit more. This vertex comes, we now see its rank 2. We immediately know that this one, whichever is its rank, is going to query 2, and then we also call this one settled. Vertex 3 comes, its rank is revealed. It's not in MIS. We knew that. We knew that because it was settled before. But we also know that some more vertices will query 3, but not this one. This vertex is not going to query 3. Why? Because it's settled. We know that it's not going to be in MIS, so there is no need for this one to query 3. Even though the rank of this one is, at this point, we know it's higher than 3. Okay, so this is the process. I'm doing nothing else but by revealing ranks one by one and reasoning about these very simple properties. Okay? Settled vertex, and then these red arrows, meaning that, well, eventually, if I'm asked to run LCA from this vertex, well, I will query 1. Okay, so maybe we have some more, and okay, I didn't reveal the full graph, but you get the idea. Okay, and what we would like to understand is how large is the int3 to a vertex. Actually, even more specifically, how many times an edge is queried. This last thing is what we are going to analyze now. So, yes.
Because I thought it's only queried once in this line. What does queried means?
Okay. Yes. Thanks a lot. So, say for instance, this vertex, which you don't know rank, it will query 3. Then it will query 1. So this vertex will query 1, 3 once. This vertex 4 will query 3 and then 1. So it will query 1, 3 also once. 3 itself will query 1. So it's like third time. This one will query 3 eventually, then 1. So it's fourth time, and so on. So if you actually write, if you were to write down this recursive query 3 from every vertex in the graph, then you're asking how many times one edge appears in this graph. Not in this graph, but in the union of these trees, on this query vertex. Okay, thanks.
So you're really interested in the
out tree of a random vertex, but you're going to count the in tree of every vertex, and then this.
Yes, yes, which is even, depending what you want to get, but is slightly stronger. Yes, yes, yes. Yeah, because I can multiply directly by. So let us fix AB, and we want to. I want now to set up some process. There is not much time left and not much content left, which is great. So I want to set up. I want to set up some process which will now allow me to count these things. To count these things step by step, to reason about them step by step. So let's focus on some edge A and B. We don't know about the rank of A and B at time 0. Here I'm denoting the time. We don't even know that B will query A ever, but we are interested about like this, how many times A, B will be queried. So whatever is coming to query has to come through B to A. So let's execute this process for a bit. So maybe at time t is equal to 3, we learn that the rank of A is equal to 3. Assume that B is not settled yet, so you can immediately tell that B will query A, right, at some point. Right? And maybe this process goes on at time is equal to 5. You learn the rank of B is 5, and then you might have something more, that there is also neighbor of B, its rank is 6. There is some tree which is getting constructed, and here is now an idea. This idea, as you might guess, is not going to work immediately, but it will not need that much massaging. But one attempt in trying to capture this process and then analyze. Let's take a snapshot of this at some time t, and let us try to argue that there will be not that many vertices coming from maybe these neighbors to query them and then eventually query AB. Okay, this is just a suggestion, one of the first attempt. So we are again taking snapshot of this situation, in this case after a time t is equal to 9, and then we want to argue something. So now I want to show you how this can go wrong, and then we will fix this. So the situation when this is really bad is when E, so we still don't know the rank of E, but E has many neighbors, and even assume that they're only connected to E, which are not settled. We don't know their ranks. We don't know the rank of E. So if you're in this situation, I have actually two questions. The first one is, does anyone want to tell me in times t is equal to 10, 11 until the end of the process, how many neighbors, W1, W2 up to WK, we expect to query E? And each of those which query E, they will then recursively query A and B, right? So how many neighbors do we expect? We don't know nothing about the randomness. It's to be revealed. But how many neighbors, once we reveal the randomness and replace these question marks by numbers, how many neighbors in expectation you expect to query? K over 2, thanks a lot, yes. It's exactly K over 2 in expectation, because if you ask, say, maybe W2 and E, with probability 1/2, the rank of E will be smaller than the rank of W, and if that happens, W2 will query E. But this is bad for us. I promised you constant for this, and this is clearly bad for us. We don't like this. And here is the second question. Like really, if you see the answer to the second question, we're almost done. I will just give you a formal language how to formalize this. Why is this not an issue in the full process? Remember, I gave you a snapshot at time t is equal to 9. I'm not saying this is the best snapshot. I'm just asking you about the full process without me adversarially giving you a snapshot at some time. And I'm asking you why this situation, this actual graph, is not an issue. think about time is equal to 0, or take your own snapshot. I will show you one snapshot in the next slide, but choose the snapshot that you want. Why is this not an issue? And again, what I mean by issue, I don't want AB to be queried too many times. This is what I want to avoid. I'm only thinking about AB, right, in this picture. Yes, exactly. Thanks a lot. Excellent. So I gave you again a adversarial snapshot, but think about these neighbors, W1, W2 at time t is equal to 0. It's much more likely that one node across W1, W2, W3, or Wk will have higher rank, will have smaller value in pi than C. If that happens, E will never query C. E will actually go to one of these. Maybe it's W3. Okay, it will go, say, to W3, for instance. It will never query C. So none of these neighbors, they can query E, and then they go to W3. Like it can happen. But I'm now concerned about AB. So you see, if we took snapshot, which was maybe some better time, this bad situation would actually, it would be unlikely that it happens. And is there any question on this? I hope it's clear what I'm trying to avoid and what are these reasons, right? So maybe the main message of this is let's look a bit earlier. Let's take a snapshot a bit earlier. And particular, if I take snapshot as t is, say, equal to 5, I don't want to look at only these red query paths so far, as we did previously, but I want to take one look ahead vertex, if you wish. Like I want to look slightly longer. I'm calling this query path, and I'm calling this dangerous query path. We call this in a paper dangerous extended query path, but so I'm calling this dangerous query path. It doesn't mean that E, C, B, E will be a query path ever, but it means that it has potential to become a query path and then potentially affect, by many of these neighbors. Okay, so this is my definition. Query path is what we really know by, say, time is equal to 5 that is going to be query path. And dangerous query path, again, is the query path plus one look ahead vertex, which is not settled yet. I did not try, but I want E also not to be settled. And none of this is settled. Now we are ready for actually formal setup. Just perfect, 45 seconds. So the first case, if among this C, E, W1, W2, up to WK, the rank of C is set next, think about the rank of C as being equal to 6. We don't like that. We will get one new query path, ECBA, but as SFR said, we will potentially get many new query paths in the future. K over 2. Bad. We don't like that. What we like a lot more is this otherwise case, where E never queries C in the first place. So we like that. Now, luckily, the probability of the first case happening is only 1 over K plus 1. And with this probability, we get new query paths, and all these paths, which would be A, B, C, E, and then these look-ahead paths, they would become dangerous. Again, dangerous paths can eventually become query paths, which, again, we don't like that much. Now, with probability 1, always, we lose one dangerous query path. No matter what happens, who gets chosen, this A, B, C, E will not be dangerous path anymore, because E will be settled. Right? So this is what we have. And now you write down a quantity, this one, which is I want simply to track this quantity 2 times the dangerous query paths for vertex AB, meaning those who end in AB, plus the number of query paths. And that, surprisingly, is a super martingale, meaning that if you look at its behavior over time, it is non-increasing. But at time t is equal to 0, there are no query paths, and every edge in the graph is a dangerous query path. So in the beginning, at time 0, this sum is 2. And you have super martingale, so in expectation, this at the end is at most 2. And that's it. So I hope I delivered my promise for one part of it. And so that's what you get. This is not enough for the approximation part. Someone asked about intuition. But it's slightly messier. You have to define these paths something more, so to tie them to pivot. But then similar kind of reasoning also goes through, okay, to get the approximation. But this, again, the point of this was to recreate this YYI result. And that's it. That's all about the proof, all about the algorithm. Some open questions. I really would like to see more applications of this. Again, I hope it gives different view. And from my understanding, one really nice question, but from my understanding, it is not known how to get, and correct me please if I'm false on this, but it's not known how to get LCA for MIS, which runs in poly-delta LCA queries in expectation, but for any vertex. Because what you've seen is true for vertex on average, right? So from my understanding, this is not known, and I think it's really a nice question. Here, there is no dependence on n. Just to make it clear, we know poly delta times log n, but we don't know if we remove dependence on log n. And that would be all from me. Thank you. Yes, yes.
Do we need to have a dependence on n if we have a cycle because of these distributed lower bounds of log star n, just the 3 colors of ring?
Mm-hmm. Oh, you're saying that the answer to this question is no?
Yes. I guess log star n is needed, but maybe you can improve log n too.
Mm-hmm. That's a great point.
And can you, I mean, we have the random vertex in expectation is related to delta bar.
Yes, yes, yes.
All the high probability results were related to delta. Can it be that?
It's, okay. I don't know whether I missed, whether some of people who worked on some of these results know whether some of prior work also gives you some the average. You mean whether one can get poly average of delta times log n? I don't know whether it's known or not. But yeah, if not, that's also a nice question.
Knowing because you can have a small graph somewhere, you have to be correct everywhere. So you can have you can put smaller vertices on the other side to increase the degree. Yeah, I'm actually not sure, but I thought
There are
use average degree, and the small part won't change. So you still and the large part you have to be still running an LCA.
you can add lots of singletons in the graph to bring down the average degree. I know that there are not for this exact question, but for approximate matchings, there is work trying to get average dependence on degree. Again, not for this problem exactly, but for related problem and approximation. I think you also get additive epsilon n, right? In the approximation to multiplicative epsilon n.
Okay, thank you very much.
Thank you.
We are starting.